Having looked at how we can construct Taylor polynomials, it's worth looking at a classic problem type that you'll see some examples of in your practice problems. Let's say we have a function that's not a polynomial. So we'll assume that up front. It is not a polynomial function. But someone says, well, we can approximate that non-polynomial function with this cubic near x equals 5. What that is code for, quite frankly, it is a code, you have to learn how to translate it, is that this is the cubic polynomial, the cubic Taylor polynomial near x equals 5, or the Taylor polynomial of degree 3. Near x equals 5. How do we know it's near 5? Well, look at all the terms with x's in them. The linear is x minus 5, cubic, x minus 5 cubed. And so that tells us immediately that it has that form that we expect with Taylor polynomials. And so these multipliers are going to be coming from the derivatives. So just to remind ourselves what that would look like in general, we have f of a, f prime of a, x minus a, plus f double prime of a, x minus a all squared over 2. Again, thinking derivatives have to cancel, multiply out. Third derivative at a over 3 times 2, x minus a cubed. So if you can interpret this approximation of a non-polynomial as this and this function here being the Taylor polynomial, then what we can do is just line things up. We have 7. Our function is around 7 plus, well, that's a negative 1 out front, x minus 5, plus, you'll notice there's no quadratic term. What does that mean? Well, it means the multiplier out front of it must be 0, and then we have 1 x minus a all cubed. In this case here, these were 5s, so I'll change those to 5s to be explicit. So this is what we were given, and the analogy or the mapping we're asking you to draw on is that this is how we would have gotten these particular values. So what we can read off is f of a is 7, or in this case here, f of 5 is 7. Here we can read that f prime of 5 must be negative 1. Here we can read that f double prime at 5 over 2 must be 0. So this one we have to do a little bit of calculation. F double prime of 5 must have been 0 as well. Last but not least, f triple prime at 5 over 3 times 2 is 6. That had to equal 1, so the third derivative of the function at 5 must have been 6. So again, this is a problem type, you will see it in your practice problems. We're given a function, it's being approximated by a polynomial of some degree, it could be any degree, but the pattern would be dictated by Taylor polynomial pattern. And once we fill in our function, put it right alongside what the polynomial from the Taylor polynomial would be, we can equate the coefficients of the respective powers of x, and from that we can find the value of the function, the derivative, second derivative, third derivative, up to the degree of the polynomial that we were given in the first place. So take a look at the practice problems, and hopefully that'll reinforce some of the ideas in this particular example.